Okay, in this video, we're going to be looking at something interesting that happens when you try and represent a function and its inverse on the same graph. So let's take a function that we used earlier. We had g of x equals x squared plus 2x plus 3 for the domain x is bigger than or equal to 1. If we draw that on the graph, it looks like this. We also found the inverse of that function. G to the minus 1 of x is minus 1 plus root x minus 2. That looks like this. Take a look at the graph. Can you see that the inverse function is a reflection of the original function in the line y equals x? And it turns out that that is something that will always be true. Let's think about our function g. It has to take values in the domain of g and output values in the range of g. And the inverse function has to take values from the range of g and get us back to the values in the domain of g. That tells us that the range of g is equivalent to the domain of the inverse, and the domain of g is equivalent to the range of the inverse. Let's have a look at what that means graphically then. Suppose we have our function here g, and we decide to put in the x value of 1. 1 squared plus 2 times 1 plus 3 gives us 6. By definition, the inverse should take 6 and get us back to 1. So if we put 6 in on the x-axis over here, the inverse should get us over here to 1. Now have a look at the coordinates on both of these lines. The coordinate of the point on the original was 1, 6, and if we switch the x and y values, we get 6, 1. And that's not just by chance, that's by design. So if we take any point on this original curve and flip the x and y values, we'll end up with a value that's on the inverse curve, which means that we'll always get a mirror image in the line y equals x. This can be particularly helpful if we want to find out a point where a function and its inverse meet, because if they're mirror images of each other, they will meet somewhere on the line y equals x, and that's what we're going to have a look at in the next example.